There's gold in them there hills. Okay, so what we're looking at here is what's commonly referred to as an Atwood's machine. And all an Atwood's machine is we take a pulley, we put masses over two sides of it. That's it. That's an Atwood's machine. It's nothing crazy. And that's what we're looking at here. So if you happen to fall down a hole in the ground into a cave, and you happen to find One-Eyed Bill's buried pirate treasure, maybe you have to haul it out. And one of the ways you can do that is with an Atwood's machine. You can pull down or use your body weight to pull the rope down on the pulley, and that will cause the gold to lift up on the other side. So what we're going to do is take a look at this example problem. We're going to see how it's very similar to everything we've done in this unit thus far, but just how we can be careful about directions and setting up our proper positives and negatives here. Okay, so let's take a look at this problem and dive into it. What we've got here is a 75 kilogram explorer. Okay, that's you right there. And they're lifting sacks of gold from the mine. So here's the gold, here's the explorer. And the rope is going to snap if the tension in that rope exceeds 250 newtons. Okay? And that's an issue because if that rope snaps, you're going to lose all that gold and you're not going to be able to get out of this cave. So the question becomes, what is the largest mass of gold that the explorer can lift? Because you'd like to, just lift a few sacks out and call it a day, but if it takes you too long, maybe the booby traps will go off and you'll be buried forever. So what is the largest mass of gold the explorer can lift? So the way we're going to first set this up is the same way as we do for every single problem we encounter for forces. We need to draw free body diagrams. That's simply it. If we set these up, we're pretty much done. So let's set this up for the sack of gold first. If this sack of gold is hanging here, what are the forces acting on it? Well, the first force we can think about is the weight of the bag of gold itself, because if this cable or this rope snaps, bag of gold is going to fall due to its weight. So we know that there's some weight here. We can say the weight's equal to the mass of the gold, we'll call it mg, times gravity. And remember, we use little g for gravity. Big G is its own specific little thing. So here's the mass of the gold times gravity. That's the weight acting down. Well, something has to overcome that weight in order to lift the bag of gold upwards, and that is the tension in the rope itself. So voila. And those are the two forces we have acting on the rope. Take a second here and see if you can figure out, if we've got our person over here, what are the forces acting on the person? So take a second, grab a pencil, pen, piece of paper, try to draw the free body diagram for our person. Okay, so live, we had Jack here. He told us that there's a weight of the explorer pulling down. It's very common for people to say that this is like gravity pulling down, but gravity is just a field. Remember that. It's really your weight that is pulling you down. So your weight of the explorer is equal to your mass of the explorer times gravity. That's our 9.8. And then, as was mentioned, if he's pulling down, something's pulling him up. That's the weight of gold, and it's that tension. And that tension is going to be an equal and opposite force. So remember, these tensions here are the same tension, they're equal and opposite. And in this case here, those are our two free body diagrams. That's what we're looking at. This is amazing. And okay, so we have our two free body diagrams, and at this point, we need to pick positive and negative directions. Now, you can always pick whatever direction you choose to be positive or negative, but as soon as you pick something, you have to hold that through the entire problem. Now, I always recommend choosing the direction that an object is accelerating as the positive direction. That's just my recommendation, and that's because whenever you write out your sum of the forces equals ma, that'll just allow this acceleration to be positive. That's just how I like to do it. Now, in a problem like this with Atwood's machine, we're actually going to see something interesting here, and it's going to be very similar to what we saw with the block of cheese in the mouse problem. Our block of gold is accelerating upward, but our person is accelerating downward. And they have to have the same acceleration because they're rigidly connected from the rope. So that's the acceleration of the system. So wait a second. If I said choose the direction of acceleration to be positive, that means up is positive and down is positive? Wait a second. I thought I had to choose a positive direction, and once I chose that direction, it had to be that. Isn't this breaking that in a way? So here's the explanation. If we look at the entire system moving, I'm going to prove that for the gold, up will be positive, and for the climber, down will be positive. And here's why. When I look at this gold going up and the rope going over the pulley, this is the direction of motion. Do you see how that's like a U right there? If I took this U and I unbent it, it would look like that. It would look like a straight line. And what we're essentially saying is, as long as you're following the U, you're following that direction of motion for the acceleration, what we're saying is that where that arrow is pointing is positive, and where it is not pointing is negative. When we draw this U, we can think about the arrow pointing upwards on the left side. So on the left side, up is positive and down is negative. On the right side, as we come over the pulley, because it's changing the direction of the rope, we see that the arrow's pointing down, and that means down is going to be positive over here, because that's there, and up is going to be our negative direction. So that's what's going on. It's like a weird thing, but if we think about it, as we're moving around this system, we're going positive, 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 positive the whole time. And that's what's actually going on here. So we did make a decision, but we have to be careful about these turnt systems, these huge systems for us on these pulleys, because our traditional straight line that we've always been using has all of a sudden turned into a bent line. But we still can think about the direction of things that are moving as a system. That direction is the positive direction. So once again, to reiterate, what we're going to see in this problem for us is that going for the gold, up is positive, down is negative, and then for the climber, down is positive and up is negative. Okay? Now, the choice here to this would be that if you wanted to, you could switch all of these. You could call down positive and up negative for the gold, and then for the climber, up positive and down negative. That's the decision you can make. It doesn't matter. But like I said, I like to choose directions of motions to be positive, or directions of acceleration. So this is what we get here in purple. Okay? So at this point, let's take a look at how we can actually solve this out with our free body diagrams and our directions. We need to write out, because we have two objects, we've got the bag of gold and we've got the climber. That means we need to write out two F equals ma equations. Or if you're clever and you want to just find the acceleration, then you can set up a system. But we're not going to do that here because we're going to need this tension anyways. So let's work this out. So let's set up the left side for the bag of gold first. So I'm going to put a circle around my bag of gold, and any forces I circled there better pop up into my F equals ma equation. So for the gold, my sum of the forces are a positive tension, because it's acting in the positive direction, plus a negative weight, so minus weight here. And you know what, while we're at it, we know that's the weight. Let's just replace that with mg. This is the mass of the gold times gravity. And this has to equal ma, the mass of the gold, because that's what I have here, multiplied by some acceleration. And that's the acceleration of the system. For our explorer, maybe we should just name them Dora. What are we going to have? Well, when we circle our free body diagram, we see we have two forces, a weight and a tension. The weight is positive, and you know what? Once again, let's just replace this with mg. So there's the mass of the explorer times gravity, because that's the weight, and then plus a negative tension, because that tension's in the negative direction, so minus tension, that's going to equal the mass of just our climber, because that's the only mass we contained, so me times the acceleration of the system. Okay? So right now, we've got these equations set up. They pretty much only have variables in it. What numbers could we put into this system? But if you get to this point where you have these two equations, you should feel great. You're an accomplished physicist. Like, that is the physics there. The rest of this is just some math time. So let's actually go through and get some math. We know that our Explorer is 75 kilograms. So what that's going to allow us to do is, for the masses of the Explorer, we could put in a 75 for each of these. And actually, we know gravity is 9.8. So we can actually multiply those together and get a weight real quick and set that up. So let's do that for our Explorer. 75 times 9.8 is a weird number. It is 735 minus an unknown tension equals 75 times the acceleration of the system. Okay? For the gold, well, the only thing we know here is 9.8, and that still leaves us with a lot of unknowns. We still won't know the mass of the gold, and we still don't know the acceleration. So that's a question mark on that side. But we actually know one more thing for the Explorer. We know that this rope is going to snap if the tension in it exceeds 250 newtons. So if we want to lift out the most gold possible, let's set the tension here, and likewise over here for the gold, to 250. If we do this, then we'll have the following. 735 minus the maximum tension, 250, is going to equal 75 times the acceleration of the system. And this is nice because now, in this equation for the Explorer, the acceleration is the only unknown variable I have. So I can actually solve for it. So let's do that real quick. So 735 minus 250, crunch, 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 gives us 485. That's going to equal 75 times A. And then that means I could just divide each side by 75 here. And let's see, 485 divided by 75 is, what do we got? That gives our acceleration of the system is 6.46 repeating meters per second squared. Okay, so that's the acceleration of our system. That's not the mass of the gold we want, though. That's just what the acceleration will be. But what's nice about this number is that acceleration of the system can get thrown into the gold equation. And like I said before, we know that that tension there is 250. So if we plug in some numbers up here now, the tension's 250 minus some unknown mass of the gold times 9.8 equals some unknown mass of the gold times 6.46 repeating. Well, this actually looks almost identical to the mouse problem we did, where these accelerations are like terms, and that means we can add them together. If I move the 9.8 mg over to the right, if I add 9.8 mg to each side, that will go away. And when we take 6.46 plus 9.8, we're going to see here, we're going to get 250 equals, let's see, 6.46 plus 9.8 gives us 16.26. So that'll be 16.26 multiplied by the mass of the gold. Okay? This is a little weird sometimes for students to look at because the unknown variables in front, this is the same as saying 9.8 mg. So sometimes students like to write it like that. It looks a little bit better for them. Because typically in your math classes, you write things as like 3x, not x3. So if you want to do that, that's what's going on there. That's why things look a little weird. But we are just adding the 9.8 and the 6.46 to get 16.26. That's the acceleration there. And then there's our mass. And then this means we just have one final step, dividing by the 16.26 on each side. which 250 divided by 16.26 gives us the mass of the gold equaling 15.3, and with rounding, 7 kilograms. And we know it has to be kilograms because we're in units of mass there, okay? So that was like a lot of math there at the end, but if we actually think about like what was the physics we did in this problem, we drew a picture, we picked the direction of motion to be positive, and we had to be careful because it kind of U's around, and then we set up one equation and two equations. And that was it. That was all the physics that happened there. The rest of this was us just being careful and plugging in numbers with mathematics. So if you can get up to this point where you're writing out your two equations because we have two free body diagrams, then you're in a perfect scenario to solve this problem out and be successful, okay? And with that, this is finished. Adios, great job, and take it easy.